Start recording. So it's a pleasure to have Vedran Bradar with us today. He's a postdoc at Fermilab and Northwestern University. He did a previous postdoc in Max Planck and his PhD in Mainz in Germany. So he'll be telling us about gravitational waves as a probe of new physics. So whenever you're ready, Vedran.
Thanks, Mateusz, and also to you and Raymond for the invitation. Okay, hold on. So yeah, the topic I would just like to discuss the gravitational waves as a probe of new physics in the context of several projects, in particular the North American ones, which are LIGO and Nanograph. So actually, my strategy for the talk is going to be, of course, biased toward my own research. And I'll try to offer one new physics scenario that can be probed in any of three complementary projects, experiments that are currently there or planned to detect gravitational waves. One is ground-based detectors, LIGO and Virgo, which are existing, and this is actually a picture from Virgo, which is in Italy. Then there is planned space-based detectors, and this is the envisioned picture of LISA. It would have these three detectors and these arms, which are orders of magnitude larger than this kilometer spread in LIGO. That project is the most mature among all the space-based detectors, and it's planned to be deployed in 2033. And finally, there's this pulsar timing arrays. So basically, already for like 15 years, the gravitational waves can be probed from detecting the radio waves from pulsars. I'll touch that in the last part of the talk, basically in the context of Nanograph collaboration, which recently hinted a certain discovery of stochastic gravitational wave background. But basically, the cookbook, if you're thinking about new physics in the context of gravitational waves, is essentially, and that's just the strategy we'll follow here, is to produce the stochastic gravitational wave background to compute the spectra from a given source, and then just simply compare to the existing sensitivities from various observatories. For instance, the ground-based detectors, they're sensitive here in the ballpark between order 1 and 100 Hertz. And you can see here certain lines. These are for present LIGO plus Virgo. And eventually, there will be joined with Japanese project Kagura to the design sensitivity, which is given here. There are also some future ground-based detectors, such as Einstein Telescope and Cosmic Explorer, which are only the third generation experiments, which we can probably expect toward the end of the century only. But these guys, the LIGO and Virgo, are already there. I mentioned LISA, the leading space-based detectors. The major sensitivities from those ranges between 10 to the minus 4 to order 1 Hertz. The green line, the green region here is corresponding to LISA, and there are several other planned projects which are not as mature, but they may easily happen. Japanese project DeSiGo and the Big Bang Observer. And finally, at the frequencies of around inverse year, the pulsar timing arrays are sensitive, and here we have Nanograph, EPT, and PPTA, which are currently at the sensitivities of 10 to the minus 9 in terms of energy density of the universe, and they have prospects to go all the way toward 10 to the minus 16 or so. So let me just follow that strategy I outlined, and let's start with the first model. I'll try to discuss first the scenario which can be tested in ground-based detectors, such as LIGO and Virgo. To do that, I just need to introduce the model, and I'll try to do it as briefly as possible, focusing mostly on the thermal effects and the gravitational waves. So the first model is goes by the name of neutrino option, which was proposed a couple of years ago by these authors. And essentially, they're trying to answer in a very minimal framework. Well, maybe I can be provocative and say most of the problems we have in higher energy physics. So in principle, they're trying to simultaneously generate the electroweak scale and the neutrino mass. One can motivate that by saying that you know, in the Stern model we expect the Higgs is very light, and since we expect states at the GATT scale, we have the hierarchy problem, and the scalars cannot be, we cannot forbid large potential corrections, radiative corrections. So the question is, why is the Higgs so light? That's our hierarchy problem. On the other hand, neutrinos are also very light, so they're not as heavy as the Higgs, but when we compare both the mass of Higgs and mass of neutrinos to the GATT scale, these are both essentially negligible. So the question is, can we really generate both of these with the same stroke? And these authors actually found that this is possible in not.
Excuse me, why only neutrinos and Higgs? If you're talking about this mass scale of the Higgs, then all of the standard model is light.
Oh, sure. You have, in principle, you have a certain, yeah, this is considered in their RGEs. For instance, from the standard model, you would have the dominant contribution from the top Yukawa, from the loops involving the top, which would give a certain correction to, which gives a certain correction to the Higgs mass. So this is essentially included. These kind of couplings are included in this. Let me maybe go through these 3 steps, and then it will be clear, more clear on their procedure.
But Keith, right-handed neutrino mass is the only explicit mass scale that they want to put in. That's all, and you can't put anything like that in the quark sector.
Sure, but
that's all.
You can ask the question why neutrinos are light. That's fine. That's a question. But
no, yeah,
why the Higgs is light?
It's an arbitrary thing where you say, okay, I assume that the Higgs potential vanishes or something like that at some scale.
Yeah, that's
and
correct.
Can I have it radiatively generated? And maybe the answer, yes, you can.
Yeah,
But you are at the mercy of assumptions at the UV scale, right?
No, but look, the only maybe kind of visible difference is that you have kind of you know, power-like correction to the Higgs mass, and you have logarithmic correction to fermionic mass, right? So
Sure.
in this way, no, you can say that I mean, the danger of correction to Higgs are more pronounced, while it's still I mean, kind of I would say that it's still aesthetical rather than physical, because
I agree.
yeah.
So are you going to show us what's the potential look like, or just saying, I assume the Higgs potential does not have any quadratic term, only having quartic term, or you not even quartic term?
For the moment, I'm just reviewing what these authors did, and I will basically, let me see what goes on in the next 2 slides, and then we can discuss more, okay?
I should say Ilaria Briva was supposed to give a talk last week, so that would have been a perfect setup for your talk. But,
okay, perfect. Maybe I can just say that their assumption is that Marana scale, there's a Marana, they assume the Marana scale M, and that the Higgs potential fully vanishes at that scale. So this is the assumption. What they do, they sit at that scale, they immediately integrate out right-handed neutrinos, because below that scale, they're not anymore dynamical degrees of freedom. And in doing so, you get these kind of threshold corrections. So you immediately get the contribution to the mu term and the lambda term in the Higgs potential. But you're still at the high scale, M, so you need to still do the RG evolution down to the standard model scale, down to the top quark or Z boson scale. And what they actually found, and maybe she will elaborate more when she gives a talk, is that the standard model Higgs potential is reproduced at the electroweak scale for masses of around 10 to 100 PeV, and Yukawas of 10 to the minus 4, 10 to the minus 5. So once you plugged in these 2 numbers in the usual formula for the type 1 CISO, neutrino masses, you get 0.1 to 1 electron volt result. So essentially, their point is that the answer is yes, we can do it. We can do the simultaneous generation of neutrino mass and the Higgs potential. It's just that, for instance, what we wanted to understand a bit deeper, and was this assumption of Higgs potential vanishes at M. That statement is a bit ad hoc, and it deserves certain UV completion maybe. So what we did, and the model on which I based my later gravitational wave consideration, is essentially to try to understand this neutrino option at a bit more fundamental level. And here we immediately introduce the notion of classical scale invariance. Essentially, it's a very straightforward solution if one wants to really understand why the mu term vanishes in the Higgs potential. In the classical scale invariance Lagrangian at a high scale, you would essentially start with scale-less Lagrangian, and you would only generate the scales once the symmetry gets broken. Once the scale.
Sorry, can I ask a question? Sorry, going back to the previous model. So you break electroweak symmetry because the Yukawa coupling contribution coming from the neutrino generates a negative Higgs mass squared. Is that what
Correct.
happens in this
Correct.
model?
It's actually the fermionic loop, and the minus sign is crucial. You cannot do it with the scalars because you would
Right.
get not the Mexican hat, you would get instabilities. So
Right.
this sign actually matters a lot. That's correct.
Yeah, but you need a large Yukawa coupling, right? So is that right? Or
These are Yukawas 10 to the minus 4. It's a matter of taste.
but probably because
Yeah.
you have a large mass scale. That's probably
You have a
why
large
you-
mass scale.
Yeah.
You have a large mass.
But this theory is that UV finite. I mean, in a sense that still I mean, what about say power divergences in the theory? You know, due to other contribution. So it's not UV finite, right? It still contains divergences, so it doesn't.
Of course,
Uh,
it does.
Yeah, I would say yes. I would agree that it has to have quadratic divergences to the ultimate UV cutoff of this theory.
Yeah, right. So, but then you know, kind of, you should put some kind of ad hoc. You should normalize it by physical mass of Higgs. So no matter what, right?
Yeah, exactly. Yeah.
That's correct. And,
Yeah.
you know, the input here is that the Higgs potential vanishes at M, right?
That's right.
Right,
Yeah.
right,
Yeah.
right. But it is the same as to say that you know what is the mass of Higgs, right? In certain
Yeah. Well,
I guess Vedran will tell us the model next. Is that?
Yeah, you're still discussing this model by preview. Maybe I can just briefly introduce this model with the classical scale invariance. So, yeah, the classical scale invariant model have been a very hot topic in the last decades, and there's still a kind of very strong activity there. It's in my opinion, it's one of the most minimal solutions to the hierarchy problem. So essentially, in this model that I'm introducing here, this is also ensured. For instance, we will have the electroweak scale, the mass of right-handed neutrinos, and the Planck scale, and the scale symmetry will protect the corrections of this scale to reach to be corrected in such a way that it protects this scale against the Planck scale, and this scale is protected against the right-handed scale with a small Yukawa coupling that I had in the previous slide. Those that work for the neutrino option. So the minimal scenario that we found to UV complete this neutrino option contains two real scalars, two real scalar singlets, and three right-handed neutrinos. In this classical scalar model, we cannot have Majorana mass scale from the very beginning, but it will get generated from this term once the S, which is the scalar that breaks the scale symmetry, gets a VEV. There's also a contribution, the same term, the lepton portal from the previous slide. And since now the scalar sector is a bit more complicated, there's several terms in the scalar potential, which we even simplified a bit. We put a Z2 symmetry on R just for the sake of simplicity. So
how do you prevent an M Planck squared S squared term?
Yeah. So maybe let me ask it slightly different. I have the same question as Tony, right? Is a classical scale invariance asymmetry or is not, right? At the quantum level, I think at quantum level you break classical scale invariance and you will generate the mass term. Tony, is this identical to your question?
Yeah. I mean, I'm asking, like, why can't I just add an M Planck squared S squared term to that Lagrangian? What symmetry forbids that?
well,
Yeah.
at G level, they would say it's conformal symmetry that
No, but
We have M Planck.
yeah.
yeah.
No, but it goes back. I don't know if you remember. It was Bill Bardeen long ago who argued that kind of having classical scale symmetry, you can put conditions that that UV that there is no these quadratic divergences when you're doing integration. Okay, but if you are trying to implement it explicitly with kind of regularization, whatever, it would not work. So in this way, it still becomes so this scale symmetry at the quantum level. It's still no, I mean, okay, it still looks like you enforce this. So there is no, I mean, explicit. Yeah, so I think it's what Jen is asking. I think it's related to this. So
no, I
not
fully agree. I fully agree with you, and I think it's still an ongoing debate. So in
Yeah.
particle physics community, we start with the scale-less Lagrangian, which doesn't have Max Planck. But essentially, I think the answer to your question is that quantum gravity, in order for this model to work, you need to make the assumption that the quantum gravity sets a certain scale invariant boundary conditions. And this is the work in progress by Christoph Wetterich and the guys like that who are thinking about that. But this is essentially an assumption in this kind of scenario.
Yeah. Okay.
So maybe I can just illustrate the model also, and our strategy in this kind of diagram here. And essentially, yeah, we just start from that assumption. We start from scale-less Lagrangian. Then we do the RG evolution containing both scalars I introduced in the previous slide and the three right-handed neutrinos. We do it down to the scale where right-handed neutrinos and R scalar lives. Then we integrate them out. We do a bit more of RG evolution down to the scale where S lives. S has a smaller mass than other new particles because it's a Gaussian boson of spontaneously broken scale symmetry. So it doesn't get a 3-level mass. Its mass is loop suppressed. And once S is integrated out, you again do the RGs down to the standard model, and you see what you get at the electroweak scale. So for instance, you can look at this diagram, and I think Zen, this answers your question previously about the Higgs potential. You can see this generation of the Higgs potential for one successful parameter point, where you can see essentially, I know the figure is a bit small, if you go from 10 to the 8, from the renormalization scale of 10 to the 8 down to the top quark scale, you see how nicely the Mexican cat shape potential gets generated. And our criteria for successful points are those where the standard model Higgs potential lambda and mu values are reproduced within 1% accuracy. We also, sorry?
Can I ask, from this potential, seems like it's not bounded from below at high energy. Is that right?
At high energy, I think it's not bounded from. I don't remember if this was a generic. I think it's not bounded. It may not be bounded from below. Depending on what is the values of the couplings in the scalar sector, there are more couplings which are controlling the situation. But essentially, this kind of shape here, the typical shape only shows up, even though it scales. For instance, if you can see here.
Yeah, sure. I understand you can generate the mass square term and also a correction to the quartic couple. But I agree you can do that. I was just asking what's the initial assumption about the potential form. I think there's a difference between Todd's original paper where he forbids both the quadratic term and the quartic term, and here did you still allow a quartic term, or will you also set it to 0 at the scale m?
Quadratic term gets generated in the scale symmetry breaking, and the quartic term, to be honest, we didn't start from 0. They started from 0 in the paper, but we didn't. We found that that's not essential.
But did you start with positive one or negative one?
Ooh.
I would hope it's a positive one. Then your potential is better shaped than higher energy.
I don't have that in the slides, and I must have said that I've forgotten this in the meantime. It's also connected to the strategy which we generated the correct values at the low scales, and essentially this Gilner-Weinberg procedure, which I have the slides in the backup. So maybe we can touch on that a bit later.
Okay, sure, no
At the
problem.
moment, I don't remember on the sign, but I can tell you about the portal lambda SR and Yukawas that we found successful points with order 1 values of those 2 main parameters that we use in the scans. And once you put in the extra contribution, once you impose the current constraints on the sum of neutrino masses, we get the WEV around 10 to the 7, 10 to the 8, and the Yukawas 10 to the -4, which is essentially the same the same values that appeared there on the first slide. So we essentially managed to reproduce the neutrino option idea in this more UV complete framework.
Sorry, you said that there was a paper for the scale invariant boundary conditions that from quantum gravity. You said that there was a paper already out or not?
I think this has been on. I just mentioned one author, and this is Christoph Wetterich. I think this is essentially a work at the boundaries between high energy physics and GR people. So I think that there's more than a paper, but
I see.
it's an ongoing discussion.
But it seems a bit bizarre, right? Because you've got to generate the Planck scale, but then you're saying that you have a scalar sector which doesn't see the Planck scale. So you're sequestering a scalar sector from gravity. Seems quite bizarre. Right?
Well, I don't know. It's a matter of personal preference, I guess. To be honest, I haven't worked on this. So following the literature and high energy physics strategy, people usually start from the scaleless Lagrangian. But if one wants to be honest, one needs to point out that this is essentially at this point an assumption. And for instance, the models in which you start with no scales, I think they were previously in focus because of these solutions to the hierarchy problem. But the story is not full.
No, because I think people have said this in 2 dimensions, but then but gravity in 2 dimensions is not real gravity. It's not dynamical. I seem to remember people having examples of this, but beyond 2, I don't know. So, okay, no, it's fine. Yeah, I just wanted to make sure. Yeah.
So this is more or less on the model. We can still discuss later. I have a few more slides on the backup, but I wanted to focus on the gravitational wave signature. So on top of temperature independent terms, one needs to, I'm interested in the gravitational waves from first order phase transitions. So in order to do that, one needs to add the terms that are also temperature dependent. And here we add the one loop thermal contribution for both new fermions and scalars, R and N, which are given here with these Bessel functions. And since it's known that the perturbative expansion fails at large temperatures, because you have large logs of temperature over the mass scale, what is the state of the art is to include the daisy contributions, the resump daisy graphs, actually to address that issue, which is given in this form, and also something that appears in various textbooks, including these original papers. So once one is armed with the full potential at the high energy, one can consider the phase transition. And actually, in our case, we find that in this model, we find the first order phase transition for all the successful parameter points. Just as a reminder, although I'm sure you already know, for the first order phase transition, we can look at it in this vacuum expectation value at the critical temperature, or critical temperature versus the critical temperature, and it features this kind of discontinuity at a given temperature, which essentially corresponds to the transition between false and the true vacuum. In the second order phase transition, this would not be a discontinuity; it would be a continuous function. We actually find we don't just find the first order phase transition, but we find it to actually be very strong. Strong means that this is Webb over temperature is around 1, and we often find values, typical values, even 4 to 5 or even higher. This plot is for 2 benchmark points for which later I will show the gravitational wave signature. First, before that, what I forgot to say is that in the strong first order phase transition, if the first order phase transition are very strong, this also implies supercooling, which means that the actual temperature of the phase transition can be several orders of magnitude below the critical temperature and below the Webb, below something you expect by just looking at the bare Lagrangian. And this is actually what happens, what we find in this model. The nucleation temperature, which I will call the temperature of the phase transition, is several orders of magnitude below the critical temperature. So the idea of this first order phase transition, just to briefly illustrate, is it goes via bubble nucleation. So what gets produced is the bubbles inside of which true vacuum exists. And these bubbles are growing and getting produced and spreading and trying to occupy the great portion of the universe. But the bubble nucleation rate is given by this expression, which also contains the Euclidean action of the bubble. That is something that is done solved numerically. At the same time, while these bubbles try to occupy the universe, the universe is expanding. So the universe is not cooperating. The universe expansion is just given by the first Friedmann equation. And we have here the contribution from the radiation, as well as the vacuum contribution, which is essentially the difference between the potential at the true and the false vacua. So if this term dominates, you're in the phase of exponential spread of the universe, exponential evolution, and you will actually undergo a phase of mini inflation. We actually found that in our model, all the points, successful points happen inside of that region. So it happened during the vacuum dominated era. And in fact, given this term, we actually find for many of the points that the phase transition doesn't even complete successfully. So for instance, if you look at this plot points here in the parameter space of coupling and Yukawa, the analysis at temperature equals 0 that I was discussing previously gives you all these points, but actually only those that are in this red blob feature a successful phase transition. The first order phase transition completes successfully. In all the other cases, the phase transition is so strong, you can see this V over T reaching values up to 12, that it just doesn't complete successfully. I'm not saying that these points are inconsistent, but they're not consistent with neutrino option, so I will discard them in the next slides and just give you some more dense scan of this region here. By the way, what can happen at the QCD scale, but I want to delay for this discussion after the talk, one can, even for these points in the QCD, the term linear in the Higgs field gets generated. So there is an option to break the symmetry and produce the Higgs wave later. But maybe we can, this is not connected to what I'm trying to do here, so maybe we can touch on that later, because I see from the discussion from the previous slides that you're interested in these things. So yeah.
Do you ever get dominated by the vacuum before the transition is finished?
Correct. Actually, before the reheating, the phase transition is always in for the successful points in the vacuum dominated era.
Then why don't you just start a new inflationary phase?
So during that era, before when vacuum starts dominating and before the phase transition gets happened and reheats the universe, there is a certain era of what you can call a new inflation, mini inflation. So the universe is spreading exponentially, driven by this term, and this is what prevents you, in many of these cases, to even have a successful phase transition. Only those with relatively mild, although still very strong phase transition of order 4 to 5 in terms of this wave over temperature leads to a certain successful cosmology in that sense.
Mm-hmm.
Shall I go to the next slide?
Yeah, I think so.
So I just want to briefly introduce I'm very happy of these interactions and all these questions. I just need to recalculate a bit. So we have a sharp cutoff at 1:30, or how are we, Mateusz?
I think we're more flexible, so
okay, then let me for the moment stick to the slides.
If people have questions, I have to leave, but otherwise I think it's okay.
Then let me for the moment stick to the schedule, and I can speed up at a certain point. But this slide is more or less important because here I just want to introduce the ingredients for the gravitational wave signature. And one important ingredient is the inverse duration of the phase transition beta, which essentially enters in the calculation in the expressions that are given to us by people doing simulations. So for instance, we find this beta over h, which is dimensionless, to be between 3 and 10, which corresponds to rather fast phase transition. Another crucial parameter is alpha. That's actually the dimensionless energy budget of our phase transition, which is the difference of the potential in the true and false vacua normalized to the radiation energy density at the nucleation temperature. And since we have a non-trivial contribution from the vacuum, one can actually define this vacuum temperature as a temperature where the radiation and the vacuum component would have the same strength. So below the T vacuum, the vacuum would dominate. Yeah, this given the alpha being very large number, so we have a large energy budget here. This vacuum temperature is actually equivalent to the reheating temperature. So what will happen at the nucleation temperature, the radiation energy density and the vacuum energy density will get transferred in the radiation energy density at a higher temperatures at a reheating temperature once the S field decays into the standard model particles. Here on the plot, I have in this parameter space of B, this is essentially parameter that appears in the potential. It's a term in the Coleman-Weinberg term, and actually just a linear combination of parameters involved. And the vacuum expectation value, I'm showing you these reheating temperatures, and you can see that they're between 10 to the 7 and 10 to the 9. This is already a couple of orders of magnitude higher than the TeV, where phase transitions are usually considered. So you can already see that there could be some different effects than in the typical TeV scale phase transitions. And this is actually I'll discuss this on this slide, but before that, I would just like to introduce the methods of producing the gravitational waves here from the phase transition. So one of the options is to produce it from the collisions of the shells of the scalar field. So the bubbles are essentially initially spherically symmetric, but once they collide, this spherical symmetry is broken, and you get the prerequisites for the generation of gravitational waves. The other source is directly from the plasma, from the sound waves and magnetohydrodynamical turbulences following the bubble collisions. All of these things are very heavily simulated, and here I'm essentially I'm sorry.
It's not your office.
This is not my office, but I'm giving the talk at the moment.
Yeah, but it means you have to ask. You ask.
Oh, okay. I see.
And plus, the printer office, anybody can open it for you. There's a printer office, anybody can get in there.
Sorry, I got interrupted because I'm not sitting in my office.
You got kicked out of your office? That's funny.
Yeah, I don't know. Some people came. I don't know. I'll just continue. It's a bit weird because there's a person in my office. I came here to the other office, which is always empty, but today it's not empty because some person just came. But okay, this was a bit weird.
Yeah, this is an anomaly in the COVID era.
So these people are, yeah, sorry for this inconvenience. These people I see now for the first time. What I was saying is that there are these two production mechanisms for the gravitational waves, and these simulation people are actually responsible for that. So we have the formula for the gravitational wave production given directly from the people doing the simulations. And these formulas contain the duration of the phase transition, the energy output, budget. These are all the parameters I introduced previously, as well as the parameters such as bubble wall velocity. And there's also the peak frequency of the gravitational wave signal, which is connected to the reheating temperature and the parameter beta. So this is the same plot as in the previous slide, just in terms of peak frequency instead of the reheating temperature. Here you can actually see that the peak frequencies range between 1 and 100 hertz, which is actually, if you remember from the very first plot, it's something where LIGO operates, and that will be visible from the next one of the next slides when I show the spectra. So I will be considering the LIGO and Virgo phases 02, 03, and the design phase for ground-based observatories. And for the space-based detectors, I'll be taking LISA, BBO, and DeSiGo. DeSiGo comes in 3 stages: B DeSiGo, FP DeSiGo, and Ultimate DeSiGo. That's the Japanese project, which is also planned. I said at the very beginning that one can just compute the spectra and then simply compare to the existing sensitivities. One can do that, of course, but if you want to be more quantitative, you can define the signal-to-noise ratio. So in other words, just to express the potential to disfavor or discover something in terms of sigma, and that we follow with the usual definition of signal-to-noise ratio that is here under the square root of time of observation times the integral over the sensitive frequencies over the ratio of the gravitational wave spectra and the noise. For this time of the observation, we take 5 years for the space-based detectors, and for the ground-based one, everything is well documented. There is LIGO stages 02, 03, and the design. Here is the money plot from this part of the talk. I'm essentially showing you the two spectra for the gravitational wave production, and for two benchmark points for which previously I was discussing the phase-space transition. The phase transition properties. And you can basically see that this benchmark point 1 has a peak frequency at the point where the LIGO is most sensitive. And I want to remind you that this is not tuned. This is by construction because the neutrino option lives at a certain scale of 10 to the 7, 10 to the 8 GeV. So we have a certain shift with respect to the TeV scale. If the gravitational wave was shifted left or right, the neutrino masses would be either too large or too small. So there's a certain preference for this model, and this is just by chance, but it's a very nice property that LIGO lives in that regime. Since parameters beta are different, one can expect a certain shift, and this is actually in our successful data set the lowest frequency. The parameter point with the lowest peak frequency. It's just here for completeness to see that all these future space-based detectors have a very good potential to make a discovery, because the signal-to-noise ratio with respect to BD SIGO would be order billions. You can see how strongly this enters in that region. The signal-to-noise ratio for LIGO and stage 02 is 2.7, and you need around 5. Well, literature is a bit vague, but you need a bit between 5 and 10 for the discovery. And you can see that in that sense, the benchmark point 1 is probed, but not excluded in phase 02. For phase 03, it's to be discussed in the next slide. Because LIGO and Virgo actually showed up recently with their analysis for the 03 phase. And for my plot that was well before this result, we put the 03 sensitivity here. And actually, unfortunately, the actual the results on the 03 stage is given here. And when one makes a direct comparison, they're underperforming by order of magnitude with respect to what they envisioned. Sorry for the axis. This plot was combined with another plot, and I had to cut that one because that one was irrelevant. But here is 10 to the minus 10 in terms of omega A squared. So essentially, the 03 phase hasn't improved too much with respect to the 02 phase. But still, in the next couple of years, they expect to reach the design sensitivity, which is given here. And there will be not just prospect to test this neutrino option, but also to other astrophysical stochastic processes like black hole and neutron mergers and things like that. In the context of that, this plot is a bit obsolete because these green points should be not considered as LIGO 2019-2020, but LIGO design phase. The 85% of all the viable points here, so essentially just to explain, I put here the points are, the color code is such to follow this threshold signal to noise ratio that you need for discovery. And since this number is a bit uncertain, I put here two numbers for 5 and 10. But the plots are more or less similar for LIGO. So we can look at this one and basically notice that many of the 85% actually of the points is green. And this means that those will be tested in LIGO design phase in a couple of years, which I previously anticipated it will be tested now. But as I just said, for some reason, their current sensitivity is not as strong as envisioned. You can see a couple of black points, which are actually coming from the fact that at some point you lose the sensitivity. The peak frequencies are too high or too small. But that's fine because those points are still colored in the plots corresponding to the space-based detectors. And this is essentially, this means that the model will eventually be covered by a synergy of ground and space-based detectors. Before I continue, I just want to point out that LISA, the leading space-based detector that is envisioned to operate in 2033, is not even touching our lowest frequency benchmark point. This is just because LISA actually will probe easily the TeV scale in physics, but here we shifted a couple of orders of magnitude to larger temperatures, and your gravitational wave spectra shifts, and there are no prospects for LISA. But in what follows, I can discuss quickly a model on LISA. It's just that again, okay, so yeah, I don't know what I should do at this point because I still don't want to do overtime too much. Maybe I can just quickly illustrate what we did here. So next model would be the one where symmetry breaking would happen at the TeV scale, and here the space-based detectors like LISA is something that would be the best option. So we looked at the left-right symmetric model. So this is now completely jumping from model to model. Which is essentially.
Sorry, before you move on, I just when you say test the neutrino option, I guess that's the model that you had, or is this generic?
Oh yeah, of course, this is the model I have because the previous model does not have essentially does not have a.
And are there other UV completions? I guess is also part of the question.
I'm talking about the UV completion of the neutrino option. That was just to clarify.
But are there others apart from your?
I haven't seen any other study, to be honest. I haven't seen, but for instance, for the supercooling and for the first order phase transition to be occurring in these classically scalar environment models, that's a generic property. So if these other people were to do something along these lines, and if they want to forbid the mu term just from the fact that you impose classical scale invariants, I would expect very similar results because it's the same strategy and you would have the similar first order presentation.
I understand. Okay, thank you.
So yeah, for this left-right model, I just want to be brief, and maybe I can directly just show you again. The strategy is very similar because one just needs to cook up the full potential. Containing again the thermal contributions and also the tree level and the Coleman-Weinberg terms. So the full one loop temperature-dependent potential is contained. And in order to do that, what enters are the masses and the parameters of all these, and there are like 17 parameters in this potential. So we studied that and looked for possible correlations and basically what choices of parameters we need to impose to maximize the strength of the phase transition. And we found that basically the key is in the ρ1 parameter. If ρ parameter goes down, the strength of the phase transition increases here, as you can see here. It would even be stronger for much smaller values if there was, for instance, plot in the log. So we find this in ρ1 versus ρ2, ρ3, lambda 3. So ρ1 goes down, phase transition goes, strength increases. This is valuable for this final plot. I just directly jump to this final plot where for the choices where the parameter points for in the left-right model are chosen like order 1 numbers without caring what happens with the phase transition. Usually you encounter these kind of solutions which are not even touching some very, very far away ultimate dizygo stage. On the other hand, if one uses this trick with a very small row, the prospects for probing the left-right model increases dramatically. You can see here the benchmark points 3 and 4, which corresponds to the alpha, which increases 2 orders of magnitude. So the energy budget. We can understand that in a following way. One of the minimization conditions for the potential are given here. And if we ignore the electroweak scale wavs, which are all the terms apart from the first one, you essentially have this relation here. And if rho goes down, your model approaches this scale invariant sector, right? You're losing mu, and it's much smaller than the V. So the sector goes toward the scale invariant limit. And in the previous slide, I was actually, in the previous part of the talk, I was discussing the model of neutrino option, which has a very great prospects for the gravitational waves. So my joint conclusion from this first part of the talk is essentially that if there is some future discovery at the gravitational waves facilities, which you cannot associate to some astrophysical to any stochastic gravitational wave background from astrophysics, this could put forward the models featuring this scale invariance and such dynamics. So that's my main conclusion in the first part. So in the next part, I'm discussing gravitational wave from other source, and I hope to be relatively brief on that, but just go ahead if there's some urgent questions on this part. Okay, if not, in the last part of the talk, I will discuss some very recent work on gravitational waves from topological defects. And what I use here is the pulsar timing array, PTAs. Pulsars, these are magnetized and rapidly rotating neutron stars, which produce radio waves. So these radio waves can pass through the region where gravitational waves have propagated. And since gravitational waves are essentially the disturbances in the space-time, this signal to Earth can come either sooner or later than expected. And this delay, or even going before, so this shift in the arrival times of the signal to Earth is the core of the sensitivity to the gravitational waves. The pulsar timing arrays, currently we have Project Sparks in pulsar timing array in Australia, which monitors 25 pulsars, European PTA 42 pulsars, Nanograph, which is the North American project, 47. And this is actually the catalog of Nanograph. They started around 2005. You can see that they're gradually looking into more and more pulsars. Some are very recently added to this catalog. And I will, in what follows, I will chiefly focus on Nanograph. So in the first slide, I was discussing how these constraints from the pulsar timing arrays are at the level of 10 to the minus 8 in the energy density of the universe, fraction of the energy density of the universe. But here I actually discussed briefly something that appeared a few months ago, last year, and it's still pretty much alive to the best of my knowledge. And that's the hint of Nanograph, which is reported a so-called strong preference for a stochastic common spectrum process in their recent 12.5-year dataset analysis. What does it mean? This means that one can actually, they found a great statistical preference for the scenario where you can associate the observation to a given gravitational wave, stochastic gravitational wave background on top versus the case where the signal would just be some uncorrelated noise from all the pulsars. So it looks good, but there's still things to understand, and we cannot claim any discovery because they have not found quadruple or spatial correlations, which is the missing piece. So in the interest of time, I can just skip this slide because I had some little arguments here on these correlations, and but essentially those correlations across all the pulsars would be necessary to establish the gravitational wave discovery. And for the moment, statistically, there are the p-value level of the 5%, and for the discovery, you need p-value of 10 to the minus 7 or so. That would correspond to pi sigma. So in that sense, we are relatively far away. But in any case, the hint is interesting, and it triggered some a lot of interest in the high energy community. While I want to skip that slide, I want to discuss a bit more on this slide. These are also the plots from the collaboration. You can actually see what is plotted here is the log of the residual. This is essentially their power spectrum estimates for this spatially uncorrelated process. So they model their signal essentially with several options: free spectrum. These are these violin plots. Broken power spectrum. You can see it here in blue. Power law, broken power law with only 5 frequencies involved, and power law with 30 frequencies involved. You can basically see that power law with 5 frequency involved and the broken power law agree well with the case of free spectrum, whereas this power law with more frequencies involved gives different results. This is because if you consider, if your signal is basically contained in these frequencies here, and if you have contributions from very large frequencies elsewhere, you're essentially you get a bias from the large frequencies. You get a wrong result because you're also partially driven in your fit by these frequencies that are there included in the analysis, but nothing is actually going on there from the physics perspective. This is one of the improvements they did with respect to last analysis. So they focused on these 5 frequencies, and actually the signal contained signal is here in that region. And what they also did, they managed to reduce the noise significantly, white noise across all the frequencies. And this helped a lot to increase the sensitivities across all frequencies, in particular here where they find this hint. I also want to point out that this redefinition of their analysis is finding the median value for the amplitude of their stochastic rotation wave background to be higher than the 90% confidence level limit from the 11-year data set. In other words, they're saying that they see something now in the region which was previously excluded. So in the right plot, you can basically see the amplitude of gravitational wave spectra versus the power spectrum index. And what I'm interested in are these 1 and 2 sigma regions corresponding to the power law case with 5 frequencies. And you can also see that they superimpose the result from gravitational waves from supermassive black hole binaries. And it's something that collaboration is pointing out to explain the nanograph signal, but it still lies above 1 sigma region, and it's not entering the 1 sigma region. So it's at least interesting to speculate, are there models and scenarios which could actually give a more statistically favorable explanation of nanograph? In other words, can we somehow populate this region inside? And this was actually a work that many people did in the recent months. I will discuss my explanation from Cosmic Strings, this paper here in red. But on top of Cosmic Strings, there were also explanations from first-order phase transitions. So in the first part of the talk, I was discussing first-order phase transition at very high temperatures, but you can also cook up these things at the lower temperatures and explain this nanograph signal apparently. And this, I give credit to the paper by Schwaller and his student. There was also a paper on inflation and primordial black holes. Here, I just showed the spectrum from paper by De Luca, which appeared in PRL. This is a sort of incomplete list of references, but topic-wise, I think it's essentially covering the situation that has been proposed. Yeah, let me just then briefly discuss in the time that is left our explanation on the cosmic strings. So cosmic strings are topological defects, and these are actual physical objects produced in the phase transition, as you may already know. The equivalent of cosmic strings in everyday life would essentially be freezing water and the imperfections that we see in the ice. So these are essentially a remnant of an unbroken phase in the broken phase. And here we characterize the cosmic strings by the tension, mu, which is essentially the energy per unit length. And what is essential for the gravitational wave production from cosmic strings, and that was shown by the people doing simulations, is that the long cosmic strings can intersect and form loops. And actually the gravitational waves from these loops are much more strong than those from the long strings, which was found in the various simulations. I should, again here, take this gravitational wave emission with a grain of salt. There is an ongoing debate in the community. What we do here, we assume the dominant radiation in the form of gravitational waves, which in other words means that we assume that our string dynamics is described in terms of so-called Nambu-Goto action. And in such scenarios, the prospects for gravitational waves are, this is the best case scenario for the gravitational waves. What can also happen is that the loops radiate particles, not necessarily gravitational waves. They can radiate particles or even pseudo-Boston boson of the symmetry that gets broken. This has also been studied, and there are such options. In the models featuring unifications, you can even have decays into monopole, anti-monopole pairs. But essentially, in our case, we will work with the assumption that the dominant radiation is in the form of gravitational waves. And just in the interest of time, let me show you the spectra. The spectra from cosmic strings is such that you have a flat plateau across a flat plateau in frequencies across essentially a flat plateau across frequencies, which has a drop at somewhat smaller frequencies. The drop corresponds to the production and radiation of loops in the gravitational waves in the matter domination era, whereas the plateau comes out from the production and the radiation in the radiation domination. So what enters in the calculation for the gravitational wave spectra is the scale factor, which appears in various places. So it's expected that one would expect different features at different cosmological eras. Armed with that spectrum, and we can proceed. But I should just point out that what enters also in the calculation is going to be a second parameter on top of the string tension that I'm going to leave free and do the scan in. Is the string is the parameter that describes the loop length at formation. That one is given by alpha, denoted as alpha. So our analysis strategy for the analysis here is very simple. We essentially take the information from these plots here and the power law that was considered by Nanograph, and we can connect this to the characteristic strain, which is a function only of the amplitude and the power spectra. This strain is defined such that it has a trivial, not a trivial, but it has a usual connection to the gravitational wave energy density formula that appears very often in the literature. So now, which means, in other words, that we can express the gravitational wave energy density in terms of both amplitude and the power spectrum index. From the last couple of slides, I was arguing that we can also, for the case of cosmic strings, express this in terms of string tension and parameter alpha. Here, the string tension is just trivially multiplied by Newton's constant to make the combined parameter dimensionless. So what we do is we scan densely in these two parameters, produce the gravitational wave spectra, so the omega GW at different frequencies, and then we do ourselves the fit. And if the fit is very good approximation to the real gravitational wave spectra, such parameter points are called regarded as successful. You can see here 3 benchmark points that for which I will show the spectra, and you can already see that they appear for various values of alpha and string tension. Maybe I can elaborate this on these plots. You can essentially see that here in the parameter space of amplitude and spectral index, this is essentially redoing the Nanograph plot. I'm showing their exclusion, their 1 and 2 sigma regions for this gravitational wave hint, as well as the explanation by supermassive black holes. And you can see our results for the cosmic strings in color code. In left panel, it's, the color code is in the log of string tension. In the right panel, it's the log of loop size. You can see 2 things. First, let me emphasize that so far I haven't specified a model. So this can be U1 B minus L, U1 lepton number, various symmetries. So far in the analysis, I haven't fixed the model. And you can see that I'm finding a solution here across the orders of magnitude in both of these 2 parameters of cosmic strings. In other words, the conclusion here is that there are various UV completions that could fit this kind of scenario. This can explain this kind of hint in terms of cosmic strings. One more thing to note is just aesthetically that you can see here that essentially the whole 1 sigma region gets populated, which makes the explanation much more favorable statistically in terms with respect to the previous explanation by supermassive black holes. In this plot here, I'm just showing the same results only in terms of in the parameter space of string tension and the loop size parameter. Again, the 1 and 2 sigma regions from Nanograph. At smallest string tensions, I only see the largest loop sizes. And as the string tension increases, there we see a second solution, which comes from one certain feature in the spectra, which I can discuss later if you're interested. And at even higher cosmic string tension values above 10⁻⁷, we only see a couple of solutions. but those are nevertheless already constrained by CMB. However, the CMB doesn't cut more than 10% of our viable parameter space, as you can see from the plot. And yeah, okay, if you're wondering what is this diagonal line here, it's just a sort of a separation between what you can call small and large loops. What I should say that on the same day appeared the paper by John Ellis and his collaborator Marek Levitsky, same day, the same paper on the same topic, and we find the agreement. They fix the loop size instead of let it float to 0.1, so we can only compare our results here, but we find essentially 5 to 10% discrepancy. So this is very satisfactory. I'm over time officially, but this is essentially my last slide, next to last slide, but next one I'm going to be very short. So here I just want to show the final gravitational wave spectra from these 3 points. If you look more closely, you can actually see that all these 3 lines for these 3 vantage points intersect the yellow region. The region is this is just a feature from the fact that this nanograph constraint is from the 11-year data set. And I said previously that now they see something where in the region that was constrained in their previous analysis. So it's going to be really interesting to see what goes on in the next months and years. Further statements from nanograph, but also what is necessary and I think doable is the statements from the other pulsar timing array experiments. Because as you can see, they're already at the sensitivity which matches nanograph, and they should be able to make a statement about that. If they, for some reason they don't, this nice feature of the cosmic string spectrum, the flatness across the frequencies, is something that can be tested in across several different experiments. For instance, you can see how strongly the LISA is, for instance, intersected, and the signal to noise ratio for this is bigger than 10,000. LIGO, on the other hand, you can see that LIGO design sensitivity is not really touching our benchmark points. I mean, our spectrum is not intersecting the sensitivity, their design sensitivity, but there is even a solution to that. My collaborator also wrote another paper, including metastable cosmic strings, where the model where the model would be embedded in the guts, and you would have the monopoles. You would have the channel of string decaying into monopoles, which would essentially cause a suppression of the spectra. If the spectra is suppressed, to explain nanograph, you need to crank up the string tension parameter, and then you actually end up with a solution, and they're given here in blue and green for various decay parameters, which are actually entering above the LIGO design sensitivity. So there's in this with regards to the cosmic string explanations, there's a lot of all the previous experiments can say something about it, as particularly due to the presence of this nice flat plateau coming from the production of gravitational waves in the radiation domination era. So thank you very much for the attention so far. I just can summarize now the full talk, and here I just summarize the second part. The nanograph hinted the evidence for stochastic gravitational wave backgrounds, and we here shown that it has a very nice interpretation in terms of cosmic strings. Maybe this is a first step in the forthcoming confirmation of cosmic strings. Cosmic strings, by the way, could also be produced in dielectric symmetry breaking, but here our results are indicating phase transition at a very high scales. In particular, with the string tensions that we need to explain nanograph, we're talking about 10 to the 15 GeV scales, which are the order gut. And this is maybe the main message of this talk. We have a lot of terrestrial probes and a lot of constraints being made with the sub-EV physics. This option with the gravitational waves can complement that and say something about the scenarios that live at the super high scales. The caveat to that is that if you want to make a discovery, it's always hard to pinpoint a model. But you know, regarding constraining models, this is, in my opinion, very valuable. For instance, if I can touch again at the very end to that neutrino option model, we're talking about sterile neutrinos at 10 PeV, which we cannot in particular probe anywhere else on Earth. And we have a certain sensitivity, and you saw that that model is getting probed by the gravitational waves. And yeah, I want to thank you again for the attention. And if you want, we can further discuss now. Oh, okay, let me go back.
Yeah. Thank you, Vedran. We'll just give some virtual applause.
By the way,
Are there any? Yeah.
No, I was literally shocked in the last part of the talk because this person came here and yelling, and I mean, since that happened, I hope that I hope you guys were satisfied with the talk. But I was a bit, you know.
It was a great talk. I mean, are there any other questions people want to discuss more? The neutrino option questions at the beginning? I don't know.
I have some questions for the second half of the talk. So is there any hope at all that different sources of the cosmic strings, for example, from axion or from UMB Mansell, can be distinguished just from the gravitational wave signal alone, or are they completely identical?
Can you say it again? Sorry, you're talking about this axionic strings, or?
I'm just asking from gravitational waves signals alone. Can we tell apart where this gravitational wave is coming from, if they're coming from different cosmic strings of the axion or of other U1 symmetry? Can we tell apart just by looking at the gravitational wave signals?
So you're not talking about the interplay between the phase transition and the cosmic strings. You're talking about multiple cosmic string sources.
Yeah, or if I assume one versus the other one, is there any difference in terms of the gravitational wave signal?
So what would separate them in the spectra definitely would be the scale of symmetry breaking. That's why I cannot say that my model here is explaining, you know, the electroweak cosmic strings from electroweak symmetry breaking, because we know that that doesn't happen at the 10 to the 15 scales. But if you so I think the answer is maybe the scale separation is crucial here to distinguish the spectra. If you have something living on similar scales, or if the symmetry breaking happens in some sequential way, several symmetry breakings very prompt one after another, then I'm not sure, but also these different features have different spectra. For instance, in the cases for axions, the spectra could be a little bit different. And also, there could be also various, you know, here on the slides, I was discussing the various UV complete model that would feature different string tensions and loop sizes, but there are more other features that such strings in a given model could have, which would distinguish from one another. For instance, some of the strings could carry charge or currents, and in those cases, you would also expect different results. So I don't know if that answers your question more or less.
Yeah, that answers the question. Thanks a lot.
Sorry, so I have a question about your model again. I mean, you were connecting it to the neutrino option, but can't you just put a model at any particular scale and put in a first order phase transition? And
no, you cannot actually. That's
because I missed that, because maybe you said that.
Yeah, you cannot. This is
what's specific to the neutrino option that makes your model work? Because yeah, sorry if you said it, I must have missed it, because so I can just put any phase transition up at 10 to the 7, 10 to the 8 GeV, and then if you find a signal, be great, right? Then you can eventually you can understand it.
I think you're referring to the fact when I showed this plot and said that this is not by accident, it's by construction, right?
Yeah.
So there are two formulas, and if we ignore all this RG evolution, this can be understood in a very simple way. So if you just express the Higgs mass square as a correction from these neutrinos would be Yukawa squared times m squared over 4 pi. And from the type 1 CSEL formula for the neutrino masses, I'm not even sure if I have that formula, but that goes like Yukawa squared times Webb squared over m. If you want to explain the mass of Higgs that we know and the mass of neutrinos whose order we know, you get only one solution for M. I mean, take one solution with a grain of salt, but you get the scale and the Yukawas from that. It's fixed in that sense. These two equations fix the Yukawa and the mass of Aitken and neutrinos. There are caveats because there are RG evolution and everything that goes on, but essentially from these two expressions, one can understand. So maybe I should. I'm sorry, I didn't even include the formula for the C sub type 1 here. But essentially, given the knowledge of the Higgs mass and the neutrino masses, the scale of neutrino masses, you can infer the Yukawa and mass that you need and that's 10 to the minus 7. So if you want 10 to the 10, you can explain the Higgs mass by smaller Yukawa, but you cannot do anything for neutrinos then. Then your neutrinos are virtually massless, and you need another source for generating neutrino mass. Is that more or less understood?
Yeah. So that's what I'm saying, right? You could always make a model that has a first order phase transition, and then you can always see it, right? That was my point.
If you, of course, that would go a bit. That would be a generalization. You can always construct a model that is consistent from the Higgs perspective, but say that neutrino masses are coming from somewhere else.
Yeah.
That's fine. That's fine.
No, because all you need is just some first order phase transition. So
right. I mean, all those classes of models, you can then probe at LIGO. Every strong phase transition that is at such scales of 10 to the 7, 10 to the 8 DeV. It's just that it's hard to make a discoveries, right, in this business, because you have only a couple of observable parameters, which are alpha and beta. And the parameters in the potential, the full Lagrangian that has at least, order 10 parameters. So for constraining, I think this is, in general, very nice. For making a discovery is difficult, but for making a constraint is very nice probe. But also, I don't know if you have some. Okay, so I think it's similar for most of the experiments, to be provocative, because if we now on Wednesday learn that there's some 5 sigma in G-2, it can be anything, right? We don't know what is the model. So unless we find some resonance at some collider, you can again have multiple of explanations. So in that sense, I don't think the gravitational waves are actually far behind from qualitative perspective from terrestrial experiments.
I see. By the way, do you have some inside information? Because you said 5 sigma.
Unfortunately not.
Oh, okay. I thought you had a slip there.
Yeah, you hesitated. Sounds like you know something.
Yeah, you know something, right?
Yeah.
So I'm organizing on Saturday. There will be next Saturday there will be a talk. So okay, let me try to stop sharing. On next Saturday there will be a talk. We're organizing this PICIMO. I guess some of you guys were invited. Maybe you also registered. We just arranged for G-2 talks from one of the postdoc, but you will know the result on Wednesday, so a few days in advance. So this is all I have in touch with G-2 people, because I had to find a guy. Actually, you know what? I asked.
You know what? I'm gonna stop recording, and then you can feel free